The problem I'm doing in the book is problem from chapter 4, problem 31, and it's write the Hamiltonian for a planar pendulum and obtain Hamilton's equation of motions. So to start, the Lagrangian for this pendulum is the potential energy just depends on the gravitational force. So U is equal to mgy, where y can be solved for in terms of L cosine theta. And y0 is the lowest point. So that can be y0 is equal to L cosine of 0, which turns into 1, or turns into L. And then factoring out L, the potential energy turns into mgl of 1 minus cosine theta. And then for the kinetic energy, is 1/2 of m ds squared, where ds is equal to dr squared plus r squared d theta dot plus r squared sine squared theta in the phi dot. So because phi dot, there's no movement and the radius is a constant, ds squared turns into r squared d theta dot, where r squared is equal to L squared. So the kinetic energy turns into 1/2 of ml squared theta dot squared, and the Lagrangian turns into 1/2 of ml squared theta dot squared minus mgl of 1 minus cosine theta. And then so the Hamiltonian is written in terms of h is equal to p theta dot minus the Lagrangian. So solving for the time derivative of the partial derivative of the Lagrangian with respect to theta dot, that turns into ml squared theta dot is equal to p. And rearranging that, theta dot is equal to p over ml squared. So plugging that into the Lagrangian for all of the theta dots, the Hamiltonian turns into p times p over ml squared minus 1/2 of ml squared p squared over m squared L to the 4th plus mgl of 1 minus cosine theta. And then distributing and canceling out terms, the Hamiltonian turns into p squared divided by 2L squared, p squared divided by 2ml squared plus mgl of 1 minus cosine theta. And then to solve for Hamilton's equation of motions, the first one is theta dot is equal to the partial derivative of the Hamiltonian with respect to momentum. And that turns into, that only hits the first term in the Hamiltonian, so that turns into p over ml squared, which is exactly what we got from taking the momentum earlier. And then negative p dot is equal to the partial derivative of the Hamiltonian with respect to theta. And that turns into mgl sine theta, where the derivative with respect to theta of negative cosine is sine theta. And by moving the negative term onto the other side, the p dot is equal to negative mgl sine theta. So this is this equation is very useful in quantum mechanics for trying to solve the Schrodinger's equation.